Hello and welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition. We're doing problem number 3.25. A gaseous mixture of carbon monoxide, carbon dioxide, methane, and nitrogen is analyzed with a gas chromatograph. See problem 3.26. The output appears on a strip chart recorder as shown here. Okay, so then they have like a wave, kind of like a sine looking wave, but it has certain peaks for the different chemicals, and it has a certain area that it gives to us based off of those chemicals. For each of the 3 species, the area under the peak is approximately proportional to the number of moles of the indicated substance in the sample. From other information, it is known that the molar ratio of methane to nitrogen is 0.200. Part A, what are the mole fractions of the 4 species in the gas? From the problem statement, we also know that the area is proportional to the moles. This sign is a sign to say the area is proportional to. And then we've got, they also gave us this relationship between methane and nitrogen. Okay? We're trying to figure out the mole fractions of each of the species for part A. In order to determine what the mole fractions of the species are, let's use the information that they gave to us about how the area under the curve is proportional to the number of moles we have. For carbon monoxide, they gave us that the area under the curve is equal to 40, and it's proportional to the number of moles, so I put a constant A as the proportionality constant between the number of moles and the area under the curve. For methane, we have 25 area under the curve, and I have a new proportionality constant, B, multiplied by the number of moles. They also gave us another piece of information about methane, saying that the mole ratio between the number of moles of methane and the number of moles of nitrogen gas is equal to 0.200. So we can combine these 2 equations and form a new equation for nitrogen gas. This equation is a result of substituting this equation into this equation and rearranging some of the variables. Finally, we have our last mass balance. Our last mass balance is carbon dioxide with the last proportionality constant, C, 80 area under the curve equals a proportionality constant times the number of moles of CO2. Okay, so let's combine all of these into our total number of moles. Here I've combined the total number of moles for the total gas stream, and then I've substituted in all of the equations that we know, the relationships between the different elements and their areas under the curve. We, as of right now, don't have enough information to solve this problem, so we'll need to make a few assumptions in order to solve for the different variables. We can assume that A, B, and C proportionality constants are all equal to each other, that the gas chromatograph responds the same amount to each of these gases, and that's a fairly good assumption because each of these gases are fairly similar. So if we assume that A equals B equals C, we'll just have 2 unknowns in this equation, which is the total number of moles in the gas stream and the proportionality constant. We can also assume that we have a certain we do this problem on a certain mole basis, and if we assume that n equals 1, that we only have 1 mole of, we've sampled 1 mole of this, the gas mixture, then we can calculate what A is based off of that assumption. Okay, so we're doing this on a 1 mole basis, and we can calculate what A is. So using the two assumptions that we made, we've now calculated that the value of A is 270. From now that we know what the value of A is, and we're doing this on a 1 mole basis, now we can calculate what all the mole fractions are. Here we have that the mole fraction of carbon monoxide is equal to the number of moles of carbon monoxide divided by the total number of moles in our sample, which equals 40 divided by A. And that is the mole fraction for carbon monoxide. Then you repeat this process for each of the other elements. For part B, it says, what is the average molecular weight of the gas? Well, in order to calculate the average molecular weight, we have a formula for that. The average molecular weight is equal to the sum product of the molecular weight of the species times the mole fraction of the species. We just calculated what all of the mole fractions were. Now we just need to look up what all the molecular weights of each species are. The molecular weights of each of these species can be found in the back of the book. Now we have all the information we need in order to calculate the average molecular weight. So we just plug in all of these values and we calculate the average molecular weight. We get that the average molecular weight is equal to 31.63 grams per mole. And that is it for problem number 3.25. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I hope to see you in the next video.